Hey all, today we are going to do an activity. We call this the Beanium activity, and it is going to go over average weights of isotopes, relative abundance, percent abundance, and we are going to calculate the average atomic mass of this fictitious element that we call Beanium. So you should have downloaded this worksheet at this point, hopefully. If not, go ahead and download it or print it so you can write on it. Questions on the back. Okay, so we're going to start with procedure A, where we are to measure 50 kidney beans, 50 pinto beans, and 50 navy beans. I already have 50 of each weighed out in these 3 cups right here, and we have our scale. It is zeroed out, and I have it in grams. And so we are going to start with our kidney beans. So for procedure part A, number 1, on that line, you're going to write 15.6 grams. So that's how much 50 kidney beans weighs. Right? Next, we're going to do our 50 pinto beans. And for that, we are going to get 18.3 grams. And that should go on number 2. All right, and then for number 3, we have our navy beans. And I'm in a mess. Let's see. Sorry about that. All right, and we get 9.2 grams for that. All right, so now what we're going to do for number 4, you should actually have 3 answers for this question. And what we're going to do is we're going to take that whole number for the grams that we got, and we're going to divide it by 50 to get how much the average 1 kidney bean will weigh. Then we're going to do the same thing for pinto and for navy. So again, number 4 should have 3 different answers. You take each of those weights we just got and divide each of them by 50. All right, then we are going to go to part B. We're going to do it slightly different. I already have my random sample of beans. Okay, so you can see we have kidney beans, pinto beans, and navy beans all mixed up. And this is going to be our sample of beanium. So for our purposes right now, we are going to say this is all of the beanium that exists in the world. We're going to figure out what percentage of it is kidney beans, what percentage is pinto beans, and what percentage are the navy beans. All right, I'm just separating them out. I already have them counted for you. So in that very first column, under total number of atoms in your chart, you need to write these numbers. For kidney beans, we have 28. For pinto beans, we have 20. And for navy beans, we have 34. All right, so those are our number of total atoms. So each of our single beans is an atom. And now we're going to get the weights of each of these. So on your sheet where it says mass, for that column, I want you to draw a line straight down the middle of it. Okay, I'm going to show you. A line straight down the middle. And on the first side, you're going to write total. And then on the other side, you're going to write single. I know this is showing backwards to you. I apologize. But you get the point. Okay, so total mass, single mass. So we're going to weigh each of these and get the total. And then we're going to divide by the number of atoms of each one to get our single. So we're going to start with our kidney beans again. So the number I'm about to give you goes in that total mass column. And that number for your 28 kidney beans is 8.7 grams. 8.7, right? And now we can do the pinto beans. So 20 pinto beans will be 7.0. 7.0 grams. All right, again, we're still working in the total column. Now we're going to do our navy beans. So for 34 navy beans, we get, let's try to decide, 6.2 grams. 6.2. All right, and so now, to get that mass of a single atom, you're going to take that total number and divide by the total number of atoms. So for this first one, you take your total mass of kidney beans and divide it by 28. That will give you your single mass. Go ahead and just round to 2 decimal places and make sure you're including your unit, which is grams. All right, once you do that for those 3, we are going to move on to finding our percent abundance. So the way we do that, we are going to take our total number of atoms of all 3 isotopes and add those together. So that is going to give us our total number of atoms of beanium. Then we will take our total number of atoms of each isotope, divide by that total number of beanium atoms, and whatever you get, you're going to multiply by 100, and that will give you your percent. All right, so we're going to come over here. I'm going to show you on the board. So we get a total number. Okay, so this column, we're adding together, and we get a total of 82. So to find our percent abundance, to go in that column right there, we take this number, we divide by this number, and that's going to give us a decimal. You multiply that decimal by 100, and that will be your percent abundance. When you get your 3% abundances, make sure that you add those 3 numbers together and that they equal 100. If not, you need to either round up or round down any of the other ones. So just go back and check on that. All right, so once you have that, you will have this single column filled in. You will have this percent abundance column filled in. That is when we are going to use our atomic mass times percent abundance over 100, that formula that we learned yesterday in our notes with our examples of chlorine. And so you're going to multiply that single mass. You are going to multiply it by the percent abundance over 100, and then you are going to write your answer as the relative atomic mass. All right, so then once you do that with all 3, you'll have your 3 relative atomic masses. That is the amount of weight that that particular isotope is contributing to the total average atomic mass. Once you get those 3, you add them together. That is your average atomic mass of beanium, and you are completed. You can move on to the back and answer the questions. Once you finish all of that, you're going to write your lab report, and we will have calculations this time. So I wrote this as a nice little thing for y'all to look at, a sheet of what is expected to be in your calculations. So you'll need 3 different formulas for work for 3 different things for the mass of a single, where you're taking that total divided by the number. You have to show me all of your work, okay? You'll have 1 count for total atoms, where we just added them all together. Your percent abundance, you'll have 3 different formulas. Relative atomic mass, you'll have 3 different calculations for that. And then the atomic mass, which was the final one we did, you'll only need 1 thing for that. And then I added that atomic mass times percent over 100, just in case y'all don't remember how we did that. If you have any questions, let me know. Good luck, and I hope y'all are all doing well.